Hello everyone, welcome in our next video lecture. Myself Daljit Kaur, I am welcoming you on behalf of Physics Mate Easy Kota. In this lecture, we are going to study about the topic electronic devices. So, in this lecture, we are going to learn about the different types of the extrinsic semiconductor. The first one is the N-type semiconductor, which means that doping the tetravalent semiconductor with pentavalent impurity. We can take the pentavalent impurity, for example, arsenic, which has 5 valence electrons in its outer shell. When arsenic atom is added into the semiconductor crystal, it replaces silicon atom and settles in the lattice site of replaced silicon atom, and this arsenic atom form 4 covalent bond by sharing its 4 electrons with neighboring 4 semiconductor atoms. But what about the fifth one? The fifth valence electron of arsenic remains unaccommodated, so this electron loosely bound to its parent's nucleus and is detached easily even at a room temperature. So now the electron become free and it move randomly through the crystal. In this way, we add a large number of the free electrons, and the large number of the free electrons are available in the crystal when we add a small amount of the arsenic to the crystal structure. So in this type of the semiconductor, there is a large number of the free electrons. Majority charge carriers in this type of semiconductor are electrons, and the minority charge carriers are holes, which are thermally generated. Thus, this type of semiconductor is called as the N-type semiconductor, and this is the one type of the extrinsic semiconductors. Since each pentavalent impurity atom donates one extra electron to the crystal, so it is known as donor impurity. Next semiconductor is a p-type semiconductor. When suitable trivalent impurity is added to the pure crystal, for example in germanium crystal or a silicon pure crystal, we get extrinsic semiconductor, and that extrinsic semiconductor is known as p-type semiconductor. So in this case, the trivalent impurity atom, which has the 3 valence electrons, are added, and the trivalent impurity atom is also known as the acceptor atom because it creates a hole which can accept an electron from the neighboring bond. So, a trivalent impurity atom, say indium atom, which has the 3 valence electrons, when such atom is added into the silicon crystal, this atom replaces one of the silicon atom and settle in the lattice site of replaced semiconductor atom. So, this indium atom form 3 covalent bond with the neighboring 3 silicon atoms, and the fourth bond remain incomplete, which has a deficiency of 1 electron. So this deficiency of electron is called hole. So we can say in the figure also there is a creation of the hole, and this hole always behave like a positively charged particle. Then this hole start attracting the electrons from the neighboring covalent bond to fill itself. Now a new hole is created at a side from which the electron has been attracted to fill this hole. In this way, a number of holes are formed by adding more and more trivalent atom in the semiconductor crystal. So here are holes created by the acceptor atom. Hence, holes are the majority charge carriers and electrons are the minority charge carrier. The semiconductors doped with acceptor type impurity are called p-type semiconductor. And why this is called as the acceptor type impurity? Because each trivalent impurity atom accepts one electron from the valence band of the silicon. So it is known as acceptor impurity. And this semiconductor is known as a p-type semiconductor. So now the question comes in our mind, what is actual definition of the hole? Hole in actual, it is vacancy, or it is called as the absence of the electrons in the bond of the covalently bonded crystal. It has the same mass as the removed electron. It is associated with a positive charge of magnitude small e. It means that it shows the nature opposite to that of the electrons. So now here is a comparison between the p-type and the n-type semiconductor. We can clearly observe that in the p-type semiconductor there is a large number of the hole formation. So the holes are the majority charge carriers, and for the n-type semiconductor there are the large number of the free electrons which behave as a majority charge carrier. Now to recall the concept, here are few questions as assignment. Number 1, what is hole? Number 2, name a charge carrier in n-type semiconductor. Number 3, what type of impurity is added to obtain p-type semiconductor? Number 4, what type of charge carriers are there in a n-type semiconductor?
So we can classify metals, semiconductors and insulators on the basis of their conductivity. Metals possess very low resistivity, so they have the high conductivity. Whereas semiconductors has high resistivity or conductivity intermediates to metals and insulators. Like the resistivity for the metal varies from 10 raised to power minus 2 to 10 raised to power minus 8 ohm meter, and for the semiconductor 10 raised to power minus 5 to 10 raised to power 6 ohm meter. And for the insulators they have the very high resistivity or low conductivity. Semiconductors are of different types. The first one is a elements semiconductor. Like these semiconductors are available in the natural form and they are created from the elements. For example, silicon semiconductors, germanium semiconductors. These are the elemental semiconductors or element semiconductors. Second one is a compound semiconductors. These semiconductors are made by compounding the metals, like by making the compound of the two elements like germanium, arsenic. Such type of the semiconductors are known as a compound semiconductors. In this video, we are going to learn about the semiconductor devices, and there are the large number of the advantages. As they are small in size, they can easily operate at a low voltage, they consume less power, they have high life and the long durability. Band theory of the solids. In a substance, as many atoms are close to each other, the energy levels of the atom form a continuous band wherein the electron move. This is called band theory of solid. We know that in an atom, the protons and the neutrons, they are taking the part in the center of the atom, that is called as the nucleus. The electrons, they revolve around the nucleus in the definite orbits, and all electrons in the same orbit has the same energy. The electrons in the innermost orbit, which are completely filled, they have the complete valence electrons, whereas the electrons in the outermost orbit, which do not completely fill that shell, are called conduction electrons. We can consider an example of the silicon and the germanium, as they have the 4 electrons in the outermost shell. So now we can classify conductors, insulators and semiconductors on the basis of the conduction band. So depending upon the respective position of the valence band and the conduction band, first of all we are going to study about the conductors. The conduction band and the valence band partially overlap each other, and there is no forbidden energy gap or no any energy gap in between them. The electrons from the valence band can easily move to the conduction band, and hence large number of electrons are available in the conduction band. So for such kind of the materials, their resistance is low and conductivity is high. For insulators, we can see that a large energy gap exists between the valence band and the conduction band. The energy gap is so high that the electrons from the valence band cannot move to the conduction band. So there is no electron in the conduction band, so electrical conductivity is not possible. Now for the semiconductors, we can say there is a finite but a small energy gap exists between the valence band and conduction band. At room temperature, some of the electrons acquire energy and then they go to the conduction band, and hence they have some little bit conductivity but not more than the conductors. Hence at a higher temperature, they show the high conductivity as more number of the electrons can move, but their conductivity always lie between the conductors and the insulators. Their resistance is also not high as the insulator, so they lies as the intermediate between the conductors and insulators. So there are the two types of the semiconductors: intrinsic semiconductor and the extrinsic semiconductor. So for the intrinsic semiconductor is the pure semiconductor free from impurities. So also they have the low conductivity, and their conductivity is known as the intrinsic conductivity. So we can consider the example of the pure germanium and the silicon. Both have the 4 valence electrons. One thing to keep in the mind that semiconductors always have the 4 valence electrons. So when the temperature is 0 Kelvin, so in the crystal structure of germanium, or we can take the example of the silicon, 4 valence electrons form the 4 covalent bond by sharing of electrons with the neighboring atom. Each covalent bond is made of the 2 atoms, each from 1 atom respectively. By forming covalent bond, each germanium atom in the crystal behave as if the outermost orbit of each atom is complete with 8 electrons, and they have the no free electrons because they create a bond by sharing, and there must be the 8 electrons in the last shell. And what happens at a room temperature? The conductivity is possible at the room temperature if the electrons break away from the covalent bond and are free by the thermal energy. When electrons break away from the covalent bond, then empty space or vacancy left in the bond, that is called as a hole. An electron from the neighboring atom can break away and can be attracted by the hole, creating hole in their respective place. So hence we can say that in a crystal structure, we see electron break the covalent bond and they keep moving. Similarly, due to the attraction of the hole and the electron, hole also keep moving in the crystal. So thus breakage of a covalent bond produce one free electron and one hole in the crystal. In an intrinsic semiconductor, the most important thing that number of holes is always equal to number of the electrons. As many number of the holes are created, that are always equal to the as many number of electrons that break their bond. So Ne is equal to NH is equal to Ni. Ne represent the density of the number of the electrons, NH represent the density for the number of the holes, and Ni represent the number density for the intrinsic semiconductor. And for the energy band theory, there is an energy gap of about 1 electron volt between the valence band and the conduction band. At temperature 0 Kelvin, in terms of energy band theory, the valence band is full, but the conduction band is empty, as no electron is available in the conduction band for conductivity. So the crystal behave like electrical insulator. But at room temperature, thermal vibrations of atoms provide energy to the electrons in the valence band to cross the energy gap and moves into the conduction band as the free electrons. This result in the electrical conductivity of the semiconductor. As the electron moves from the valence band to the conduction band, so there is a vacancy created in the valence band, and this vacancy is known as hole. As the electron moves in the conduction band, the hole moves in the valence band, and the electrical conductivity is possible. So in this way, at very high temperature, when electric field is applied, the hole move towards the negative potential, giving rise to the hole current, and the electron move towards the positive potential, giving rise to the electron current. Now the second, what are extrinsic semiconductors? Extrinsic semiconductors are not at all pure. These are those semiconductors which are made by doping a pure semiconductor with the impurity. They are of the two types, N-type and P-type. In N-type semiconductor, the electrons are the majority carriers while the holes are the minority carriers. Whereas in P-type semiconductor, the holes are the majority carriers while the electrons are the minority carriers. Thank you for